we will be looking at trapping rainwater problem and find a solution in JavaScript using dynamic programming. First, let us understand the problem statement. We'll be given an elevation map represented by this graph that we can see, and we have to see after raining how much water can be trapped within this elevation map that we are receiving as an input, and the elevation map will be received as a height input with which we will have to work with. And what we can now do is try to come up with a solution wherein we try to find out what is the highest amount of water that can be trapped within this elevation structure that we are given. With dynamic programming, what we can do is try to go from the left side of the input that we have received all the way to the right side and try to find the highest possible elevation that you can find up to that index. So if you are at index 0, try to find the highest elevation at index of 0 and keep on going similarly all the way towards the right. And we will also go from the right side towards the left side and try to find the highest elevation up to the index that we are keeping on coming from the right side. So you go from the left to the right side and from the right to the left side, and this two input that will be having the highest at that specific index, from this we will pick the minimum value and then try to see against the elevation map that we have received and try to get a value. Let's see how that will look in terms of implementation. So we will just say that use a leftmost max tracker that will be array that will also go from the left side to the right side. That's what we said. For the 0th index that we have here, we will just pick the value from the elevation map, because for the logic that we are using with dynamic programming is that we will be using a base case, and from this base case we will keep on accumulating and try to get the maximum height possible at a specific index. And to do that, what we will be doing is just say pick whatever the height you have at the 0th index, and then for the next index we will pick the maximum of the current index that you have and the previous index that you had. So here max between these two is 1. Similarly, I will try now to pick between these two what is the max, which is also 1. Between these two now the maximum is 2. Between these two max is still 2. Between these two also it's 2. Between these two maximum is 3. And between this and this maximum is still 3. Between this and this maximum is still 3. This and this max is 3. This and this max is also 3. So this way we accumulated a leftmost max map in a array. This is where the concept of dynamic programming comes into picture. We start with a base case and then we keep on accumulating the highest value that is possible at our index. If you have found a higher value, that will always stay unless you find something that is much higher, and we will just keep comparing the current and the previous values to try to see what is the highest possible height that you can have at a specific index. Similarly, we will keep a rightmost max tracker. So we said we will go from left to right, which we went. Now let's go from right to left, and we will almost have the similar logic where we will say that when you are at the rightmost end, just pick whatever is there in the elevation map. So we will just pick 1 here, and then similarly I will keep comparing the rightmost value of the current index with the value in the elevation map. So I will compare this and I will compare this, which is the highest value. It is 2, so I will just pick 2 here. Then I will compare this one and 2. 2 is still higher. I will compare 2 and 2. 2 is still higher. I will compare 3 and 2. 3 is higher. 1 and 3, 3 is higher, 0 and 3, then I will again compare 1 and 3, I will compare 2 and 3, I will compare 0 and 3 again, which is higher is still 3, 1 and 3 again gets compared, and then 0 and 3 again gets compared. So this is the rightmost max tracker that we have. So using these two arrays that we have formed now, I will say now I want to have the minimum from these two at respective indexes, and then I will subtract the elevation map height from that, and let's see what we get from there. So I will say just find the minimum between these two. Minimum between these two is 0 that we have, so I will put 0 here. Minimum between these two is 1. Minimum between these two is also 1. This 2 is 2. This is 2. This is also 2. 2. Here we just have 3. Here we have 2, 2, 2, and 1. So this is the minimum that we could find between this two that we have. And then what we will do is subtract the height that we have from the elevation map and see what we get. So I will say this minus this. So 0 minus 0 is going to give me 0. 1 minus 1 is also going to give me 0. Now let's try to observe what these values can possibly indicate. Here there is no elevation and there is no rainwater also being trapped because we don't consider value outside this bounds on the left side and the right side. Then what we will say is 1 and this 0. I will subtract this 2. I will get 1. Now you can notice here that within this gap that you have water that is being stored, and we got 1 here. Then I will again go forward and I will say 2 minus 2, which is 0 again. I see there is no water being stored here. I will move forward. I will say 2 minus 1. I will get 1. You can see 1 block of water that is getting stored here, which is equivalent to what we have found. Then similarly, I will say 2 minus 0 is 2. 2 blocks of water that you have. 2 minus 1, you will get 1. 1 block of water again. So 2 and 1 here. Then here we will say 3 minus 3, which is giving us 0. Then I will say 2 minus 2, which is also giving us 0. 2 minus 1, which is going to give us 1. 2 minus 2, which is 0. 1 minus 1, which is also 0. And we ended up with this values which are now corresponding to where water has been saved. And this we will just add up. 1 plus 1 is 2, 2 plus 2 is 4, plus 5 plus 6. So I am going to get 6. This represents 1, 2, 3, 4, 5, 6. So we were able to find the amount of water that is going to get trapped. And this is a dynamic programming approach wherein we will first pick a base case and then keep on trying to find the highest possible height that can be achieved up to a specific index. And because we keep on having a track of the previous value, that's where the dynamic aspect comes, wherein from the previous value you are finding the next value. It creates this repetition pattern that keeps on relying on the previous value. And similarly, we went from right to left, and from both these sides then we found the minimum, which was this block that we found, and from there we gets subtracted, and then we find the amount of water that can be trapped. That's pretty much in terms of the concept that we are going to use here. Now let's jump into the coding aspect of it. First, we said that we will have a tracker which will be keeping track of the leftmost max values that we can have. And to do that, what we will do is something like this. Let leftmost max is equal to an array that we will be going from left to right. Then we will also have an array from right to left. So I will say right most max is going to be an array as well. I will have a total water trapped value which will be written in the end. That will be the outcome of a problem statement wherein we find the amount of water that can be trapped. Then I will say for the leftmost array that we are going to be building, which will be following the concept of dynamic programming, you need a base case. So for the base case, I will say leftmost max is going to be for the 0th value from the elevation map itself that we want to pick up. And then let's go from left to right as we went during the explanation aspect of it. So I will say for left, let I is equal to 1. Why 1? Because we already filled a base case. I will go from the 0th value up to the end, and instead of keeping on using the end again, I will just say something like this: length is equal to height dot length. So this will be easier for us to work with. I will go up to the length and I will keep on increasing my I value that we have. Then leftmost max at a specific index is going to be math.max of the previous value that we had, because we use the previous values and build the next value upon that, and that will be leftmost max of I minus 1 and the height of I, which is the current elevation that we have. And that way we will be having a left to right map that we built, which looks something like this. Then similarly we want to build the rightmost max map that we want to have track of, and for that what we will say is rightmost max of length minus 1. We have to also put a base case for it, which is just going to be height of length minus 1. And similarly now we will go in a iteration wherein I will say I is equal to the length minus 2, because for length minus 1 we already filled the value. I will say I has to be greater than equal to 0, and then I will keep on going from right to left. And for that I will say rightmost max of I is going to be the max between the elevation and the previous value that you had, which is going to look something like this: height of I and the rightmost max of I plus 1, which is going to be then giving us the maximum elevation possible at a specific index. We get both these elevations, so we got the leftmost max, we found the rightmost max, then we want to subtract this and then compute the value with the elevation map that we had by subtracting. And to do that, what we will say is I is equal to 0, I is going to be less than the length that we have with us, I plus plus, and here what we will say is the water trapped value that we want to find is going to be plus or equals. We said we want to find the minimum between the leftmost and the rightmost at a specific index. So I will just say leftmost max of I and the rightmost max of I. From this two get the minimum, and from that just subtract height of I, which we did here. So we found the minimum between the two, and then we just subtracted this from the height and then found the outcome, and then this outcome gets added, and which gave us 6. And that's pretty much it in terms of the implementation approach that we take. And now we can jump into the solution aspect of it in terms of complexities. So we went from left to right, then we went from right to left, then we went through another iteration here. So here the time complexity is going to be big O of n, with n being the length of our elevation map that we have. Similarly, for going from right to left also, it is big O of n. Of course, we skip one value in both of them. So it is big O of n minus 1, 1 being the constant, it is big O of n. So big O of n and big O of n. And similarly, here also we go all the way from 0 till the length that we have, which is also big O of n. So we add up big O of n plus big O of n plus big O of n, which gives us the overall time complexity of big O of n itself, where n is the input length that we have received. And in terms of space complexity, we are using this leftmost tracker, which will go up to n. We are using this rightmost tracker up to n. We are using this constant, that is big O of 1. So big O of n plus big O of n, which gives us big O of 2n in terms of the space complexity. And big O of 2n with 2 big the constant, the space complexity overall is also going to be big O of n itself. And that's pretty much it in terms of implementation. Thank you for watching. Please like and subscribe.